Anyway, I can start. So I'm here to present about the results that we had from our ISI meeting. If you don't know, ISI is the International Space Science Institute, which is in Switzerland, Bern, Switzerland. And every year they have calls for international teams to work on something for about 2 years, and they can have 2 or 3 meetings in person to work on a certain topic. And last year we replied to the call to study something about the seismicity of Venus with a whole bunch of experts, which you can see all the authors on this slide. And actually ISI now has a call open as well for the new ISI team. So if you want to propose something to work on with the team, I highly recommend it because it's really fun. So on the next slide, since it's one of the first talks this conference, I thought I could still get away with saying that these are very exciting times for Venus. And I'm very happy that many missions are going to Venus in the next decade. And, we'll learn about the surface and the atmosphere and activity, tectonic activity, volcanic, geologic. It's very exciting. But on the next slide, you will see that maybe probably, definitely, we won't learn everything about Venus. That's impossible. And one of the big things that we potentially will not learn a lot about is still the interior of Venus. And there's many unknowns, right? What would the crustal structure be? What even is the large-scale interior structure? Like, does it have a core? How big is the core? What is the state of the core? Liquid, solid? Is there an inner core? There's many, many questions. And one of the most powerful tools that we have to understand the interior of Venus, and also to an extent, its tectonic and geologic and volcanic activity, is seismology. And so on the next slide, we thought that now would be like a timely fashion to look into the seismicity on Venus. What we could predict would be the estimates and how we could possibly detect them. So our 2 main goals are of this team to estimate the expectant current level of seismicity on Venus, which has been done before, but we want to approach it from all these different kinds of angles and compare and see if we can get some kind of range of what would be likely. And then similarly, in the last few years, there have been a lot of people thinking about the amazing idea of detecting some kind of seismology, some kind of seismicity on Venus by, dream big, a lander or maybe something in the atmosphere. And we want to review the feasibility and advantages and disadvantages of all these different methods, and then make some kind of recommendation within the next year and a half or so. So next build is that we had our first ISI team meeting in Bern last week, if you want to press the next slide. And then immediately after, on the next slide, this is us in front of ISI. Yes, but because it was last week and I had to upload this by Wednesday, a lot of the stuff is very preliminary still. We actually did a lot in the last 2 days, but I'll have to show you that another time. So on the next slide, I'm just going to present briefly one of the things we looked into, which is scaling Venus's seismicity from the Earth. And for that, we're looking at the CMT catalog, which is this global catalog of earthquakes on the Earth, which has a magnitude of completeness of 5. And we're going to sort the earthquakes according to tectonic setting. And the reason why we came up with this is because on the next slide, we were very inspired by the work of Björn and Krishnamurti, which was published about a year ago, who scaled the volcanism of Earth to Venus. And Robbie already showed it in a previous talk, so I can be very quick about this, but they used a global database of volcanism. And then the next slide, there's lots of builds in this presentation. They sorted it by tectonic setting. And then the next slide, they looked at new and ongoing eruptions of up to 1,000 days in duration. And then in the next slide, they looked at a 60-day time window to see how many eruptions you would expect for the lifetime of a balloon. And then in the next slide, they found that you have about 20 eruptions you could see if you assume that it can scale directly to Venus. And then in the next slide, they extrapolate that to 120 eruptions on Venus per year. They made a tiny calculation error in this, and I figured that out because I was so excited about this that I redid their study because I just really wanted to know how they did it. And then when redoing this study on the next slide, I realized that the answer was actually, it's 42 eruptions on Venus per year, which I was very pleased with that number. And if you understand that reference, you will be too. Anyway, on the next slide, the whole point of this is that we were excited about this. And we thought, well, if you can do it with volcanism, can we also do it with earthquakes? And what would come out of it to see what happens? So we have the CMT catalog, which you can see here, and we are coloring the earthquake depth from light, shallow to dark red, which is deep. And the sorting of earthquakes was done by Guillermo, one of the team members of our AC team. And we want to sort it into different tectonic settings because then we can scale each individual setting to Venus because, well, there might be, as just discussed, some evidence of subduction on Venus, but probably it's not as much or as deep as we have it on Earth. So we need to take that into account and assess each tectonic setting a bit differently. So how are we going to do that? On the next slide, for example, we have the subduction trench in Chile and South America. And this is from the paper by Hasterok et al. In 2022. And they defined plate boundaries, which we're using, and also deformation zones around these plate boundaries. And this is the deformation zone for southern Chile, basically, in this pink orangey outline. And what you can see is that most of the subduction earthquakes fall into that zone, but some of them, the very deep ones, at 80 plus kilometers depth, fall outside of it. And we know that these are also subduction zone earthquakes because they're so deep. They're just part of the slab, very deep down, and they're very far apart from where we have the plate boundary at the surface. So therefore, we extended these deformation zones to include all of the subduction seismicity. So in the next slide, you can see what we did. We extended it a little bit. If you then go on the next slide, you can see how this translates to the entire globe. So we have polygons for subductions in green and for collision zones like the Himalaya and the Alps in purple. And then we have our main deformation zones, but then of course we have still our normal plate boundaries. So in order to sort those, we buffer each plate boundary with about 150 kilometers width. In the next slide, you can see that. And then we make sure that all of these seismicity, earthquakes are correctly sorted into their correct tectonic setting. So we have spreading centers, for example, extensional zones, which is rifts, and transform or strike slip faults. So then in the next slide, I'm going to show you the last thing how we sort is these boundaries in, like, it looks black, but it's kind of red. We have the intracontinental crust and the intraoceanic crust. So everything that's not related to a plate boundary then becomes either intraoceanic or intracontinental. And then we have our earthquakes sorted according to setting. So in the next slide, I will show you what we want to do, but didn't get to do by last Wednesday. We've done it now, but I can't show you that. So we want to scale from Earth to Venus. Here in dark blue, you can see the global seismicity of the Earth. And in the dashed light blue line, you can see the distribution, the Gutenberg Richter distribution of how many earthquakes you have for a given moment. And then in order to scale it to Venus, we apply some scaling factors. Here I just tried some very preliminary things, the mass and the mass times radius. And then you get this pink band of what, if the seismicity is directly scalable from Earth to Venus, would look like. Of course, this is not exactly the case. That is why we are sorting it into different tectonic settings. So the next time we speak, hopefully I can show you a breakdown of this dark blue curve into the different tectonic settings, and then for each one a scaling towards Venus. The big question then, of course, is how do you scale? Because do we really know? And one of the things we can scale by is surface area, for example. But another thing we need to take into account is the seismogenic zone thickness in the next slide. And that is what one of our other team members is working on. Ina Pleza, she's doing geodynamic modeling of the seismogenic volume and the seismogenic zone thickness. So on the left, she has some models of a mobile lid, and on the right, some models of stagnant lid, and she calculated in these models what the depth was of the seismogenic zone, assuming that the 873 Kelvin isotherm, or 600 degrees Celsius, is critical and like denotes the limit of where you can reasonably get seismicity. And then you see that for the mobile lid, you have an average seismogenic zone thickness of about 20 kilometers, while in the stagnant lid case, you have an average seismogenic zone thickness of 15.7, so almost 16 kilometers. So these are then the numbers that we want to compare to like the average seismogenic zone thickness on Earth, for example, and then we can use that to scale more accurately between Earth and Venus seismicity. So just to sum up in the next slide, we are the ISI International Team, Seismicity on Venus, Prediction and Detection. And last week we focused mainly on our first goal, which was estimate the expected current level of seismicity on Venus. And the things that I showed you today are two things that we looked at. We did a lot more as well, but we scaled Earth seismicity to Venus, and there will be more updated numbers to come with more exciting figures. And we also take into account the geodynamic modeling of the seismogenic volume. So thank you very much.